Yeah.
Hello. Okay. Can you hear us, Barbara? Also, today Yura is with us. You can say hi. Yeah.
Hello, everyone.
Okay. Okay. So maybe we start in half a minute. Yeah. Like 2 minutes. Yeah. Okay. So good afternoon and thanks for being here. I hope you can hear both of us clearly. So today, a part of the presentation will be given by Yura, and half of it will be by myself. So we'll switch back and forth. Um, and so for the today's session, which is almost halfway, we will now start to uh, at least come to the place where you can start working with your own data now, because I think there has been enough theoretical knowledge, and I think now you guys should uh, start playing around with your own data, start uh, trying to get it into R and look at it. So that's the aim today. Yeah. So just about the final organization for the course. So as always, everything, all the information is available on GitHub, um, and the remaining sessions are kind of planned. So the next session for this week is on Wednesday, a little bit quicker. Um, and it also requires a little bit of preparation because you need to install a couple of packages, but they should be pretty straightforward. At least installation of those packages, they're standard packages. And then next week on Monday, we'll do a little bit of on R Markdown. So that is about how you can share data with each other. For example, the notes that Yura makes are in R Markdown, so you can get an idea of how to make those things, how to share nice code with each other. And then at the end, we'll do next Thursday our Shiny apps. Right? So with these four, I mean, we'll give you examples on how to work with biology related data. But if you have your own data also, then I think it would be nice if you either work with it alongside or after the sessions, you go back and try to work with your own data. If you have any problems, then just let us know. Yeah? Because the aim of the course is that essentially you get to that level. Yeah? And so today, the whole aim of today will be how to read this kind of file into R. So from Excel, right? So we will not be saving them into, we'll be saving them into standard formats. So Excel is the most used, but we'll also be looking at CSV and other kind of formats. But we hope that we can achieve this from Excel. And then once you have your data in the left side format, today itself, we will see how to convert it from left to right and to do statistical analysis once you have it in this tidy format. Right? And so with that, I will transfer to Yura, and she will take over uh, the remaining part of it.
Um. Okay. So actually, I didn't prepare any presentation today, but I will explain one by one with some code that you can see on here. Well, first of all, before starting to load the files, on our directory, we should set the directory where the file exactly it is. We call it location on R that we would like to set or get the information about. So we will start with the get WD. It means we would like to get the information of the current directory that we are working for. And you don't have to put anything into the circular bracket. And if you run it, it will give you back the information of the input directory on your site. Do you know how to zoom in?
Yeah, Yura, you can go to View and then zoom in as much, or on Mac it's Command plus. Or in View.
Okay.
Yeah.
So this one is the first one that we used, get WD. And if you put this on the console, and it will definitely give back the directory that where you are working for. And what if this current location is not where you put your files to work today? And then we should use setWD, and we need to clarify the file information on here. But so input here and giving the directory information. Now what we need to do is giving the quotation mark that we see we would like to give input of the directory. So for example, I would like to take the location of the files, and you don't know the name of the directory. What you can do is click the tab key, and it will give the directory under the current directory. And then what you have to do is just click the enter key, and it will automatically return the directory that you want to take. And what you have to do is enter, and it will not give anything if it take the information correctly. So if you didn't get any error when you set the current directory on here, and then when you check the get WD, it will change the information of the directory. And so now we are in the directory where we put the files. If you want to check which file is included in the directory, which has been set as a working directory, you could use list file function, list.files, and just circular bracket. And you can see here, there will be 3 files that Sumit already uploaded, is saved in this directory. So we'll try to import the files first of all. The very first, we call it readr. And then I hope you guys already managed to install. So if you install before starting, actually we should load this library. So as we did the previous library and the readr. And it will not give any message if it is successfully attached to your environment. Actually, the goal of readr is to provide a fast and friendly way to read rectangular data, like tidy data that we deal with the previous. And it is designed to flexibly parse many type of data, like type of data that we are using on the Excel or whatever text files, CSV files. So we will actually in readr, what we can do is giving information of the extension of the file. Like for example, there is a one CSV file, and then you can use the read underbar CSV function. And then what we have to do is just put the name of the file. So now we don't have to take this because we are working on the current directory. So for example, I would like to give just saving the information of the file, and the operator with CSV, and then we can give a name of files. Well, let's say if we don't know the name of file in the directory what we would like to use, and then just click the tab key again, and you can see the several files. And since we're using the read_CSV format at the function, so what we have to do is taking the CSV file. And what we have to do is just click on here, and it will parse the data by itself, and it will show the information of each column. And then, is it work on your site? Can we move on? Okay, then another basic R function similar to read_R is actually this read_delim. So actually this file is used to import a file who is delimited by certain delimiter. So like data matrix with row and columns as the tidy data, but not only with the CSV files, we could import like tab delimited, semicolon delimited, several type of the data that you can. So here, for example, that we are going to see the information of the read_delim. It says, we define a table format and created a data frame from it. And here is the kind of usage, but we usually use actually the name of file and header, whether it has a name of each column or not, and what is the separator. Actually, that's the main one they used, as you can see here. Actually, quotes, we will not use it that much. And yeah, so you can check the kind of details on the help page, and I will try to manage on the R session, like example. I will use the same CSV files actually, but I will say draw to an operator, read_delim. And we need to give a name of file as CSV file does. And this CSV file has a header, let's say. So if you have a header, you can say true. If not, you can say false. And then each data which delimiter has been used for CSV files, mainly comma has been used. So if you input like this and then click it, and if the data is well imported, there will be no message coming. And here in the data, you can see they are well imported. When you use the read_delim function, actually you should be much cautious about separator, delimiter, and then whether it has a header or not. Because if you give a wrong separator, for example, so let's say, if you give a wrong separator, you can see here it has only one variable, and it would not be well separated in the end. So that's why we need to consider whether it has a header and which separator it used when the file is generated. However, most of you, when you receive the data, most of the format it will be definitely Excel file rather than CSV or text file. And on R, actually with the read the lim or read R that we use on here, it doesn't parse the Excel file. But what if we would like to work with the Excel file on R? The read XL makes it easy to get data out of Excel and into R. Actually, there is several packages to load the Excel files into R. Actually, read XL is the lighter and the much easier to deal with because most of the package using the Excel file, they have a lot of dependencies. So we need to consider a lot of things before using them. But for read Excel, you can use it with a really simple function. So we will start to attach this library to our session, and as with R or other stuffs, it will not return any message if it is well installed and well attached to your environment. So, well, and then to read the Excel file with read XL, what we will use is read XLS. Oh, actually, this one is mainly working. So here, if we check the information, it says read Excel, read both files who could be generated from Excel. So here we can see we need to give information of the file path. So path means where the file is existed. And the sheet is, if you have a separated sheet on your Excel file and you would like to import certain sheet, you should clarify this. Now, whether it has a column name, whether it has a column type, whatever, but we will not use them much complex since the files are not that complex files actually. So you can check the arguments and then the kind of requirements of the functions on the help page, and we'll move on. So when you check, oh, no, not this one. This Excel generated files. I hope you guys already checked it, but this has two different sheets depending on the file. But we will start with the file who doesn't have further sheets. So I will save it as two drugs and read XLS. And we should clarify the path. But when I set the directory, actually, I already set the directory where the file is saved, so I don't have to clarify the full path. What I have to do is just giving the name of file. And since it doesn't have any further sheets, just have a one single sheet, so we don't have to clarify the information of the sheet on here. So run it, and it will not give back any message as it did. So what if we would like to check whether the files are well loaded on the live environment? That we can check with view, the large V, and X means which one we would like to check. And you can see on here it was loaded well as an Excel file. But what if we would like to load the file with a different sheet information? And let's see. Well, there will be the one another Excel file that has a 2 different sheet, and then I will check. But here, since we have a 2 different sheets, so what we have to do is we need to give a sheet information, whether it is a first or a second sheet. Okay. And then if you would like to import another sheet, then we need to give number of sheet information in here. But if the name is not proper or it has duplicated name, it will change the information by itself, since R doesn't allow to have a same name of column name or row names actually. And also, if we know the worksheet that we are working for and we would like to import it, and then actually we could give the name of sheet that we set when we are working on the Excel file. But actually it doesn't work with the tab key to find, so you should clarify the precise name of the sheet. So actually I really recommend to use the name, the number of each worksheet rather than giving the name. Anyway, it works perfectly. And then let me check this one that we loaded with the read XLS and it corrected the name. As you can see on here, the column name has been changed by itself to avoid the duplicated name. And okay, so I hope everyone understands how to import the files. Okay, then what we could do is, actually we worked on the R and we would like to export the files. I will not deal with how to export Excel as an Excel format in here because it doesn't work with the read Excel and we need to install a lot of dependencies on here, so I will not work on here. I will just work with the R-based file, R-based function, I'm sorry. So this one's called write.table. Here, as you can see, write table print, it requires argument. So this argument is the one that we worked on the R, mainly data frame. So here is the kind of example, but what we are usually working with is, the first one is X, and then we need to give the name of file that we would like to export. And then what will be true or false, but I highly recommend to save as a false, because if you save the file with the quote equal true, that all the values will have a quotation mark. And the separator, this one is which separator we would like to use, like colon, comma, semicolon, tab, whatever. And also this one is kind of important one, whether we would like to export the name of row or name of column together. And it depends on your manner. Like if it has a clear column name and row names together, then you should be true for both. So it really depends on you. So for example, there was a several files I worked. So we will go on view this file. So this one called the data saved into experiment, and this one is table. So I will show that as an example how to save the data with a write table, this one into CSV format. So, I'm sorry. So here, we'll start with the write table. And what we would like to save is experiment data, and file should be, we can give any name that you want. So I will give experiment data, and the format will be CSV. Actually, the format, you can use the TS3, text, whatever you can use, but it depends on your needs and then which parameter do you usually like to use. So, and then actually bioinformaticians usually use CSV, that's why I choose it. And, oh, no. Here, what we need to do is quote information will be false because I don't want to give all the quotation mark on the data. And then separator, to separate each column, it will be comma for me. You can use like semicolon, like this. Or if you want to give it just space between it, what you can do is just click the space key one time. So it depends on your needs. So I will use the comma anyway. And then, as you can see on here, it has a column name, but it doesn't have row names. So I will give a column name. I will save the column name together, but not row names, because we don't have row names on the data. And then close the bracket, and it will save the data. If it returns errors, it means the data has not been saved. And if you want to see whether the data is well saved on your directory, what we have to do is list files, and then just empty circular brackets. As you can see on here, which one is saved is well exported. Well, actually, this example will be on the notes that I will upload after the work. So you can practice it once more with explanations. And I will turn to, I think this is all of my part that I prepared today. So I think, Sumit, you can take the further context for the tidy transformation.
Okay, thank you, Yura. Yeah, actually, I think maybe we can explain what is the difference between CSV and XLS. We just assumed that. I mean, it was we did not prepare it, but I think what I will do is I will share my screen, and I can explain to you what is the difference for people who are uninitiated between what is CSV, what is XLS format, and why sometimes it's better to save things as CSV rather than XLS. Yeah. So I'll try to just save my share my screen. So yeah. So I hope that you can see. You'll now start to see a part of my screen. Right? And so firstly, what is a CSV format? So CSV stands for comma separated version. Just 1 second. Yeah. So so comma separated version means that so all of the data is arranged in columns, right? And a comma separated version means that each column, the value in each column is separated by a comma. That's it. That's as simple as that. And the advantage of using the CSV version is that normal text editors can read it. So you do not need to have proprietary software like from Microsoft or anything like that. You can just use a normal text editor to open the files. And this is how the files look when you open it in a normal text editor, right? So this is the file. You can also open CSV files in Excel. It's not, Excel will open a CSV file. It will consider every comma as a column and it will shape it in a nice format for you. But you can also open the CSV files in a normal text editor. So here I'm just using a simple one. And here you will see that every column is now separated by a comma. And this is what we mean by a separator. So when you define a separator, what we are telling the program or any kind of reader is how the columns will be separated from each other. So if it is a comma separated file, then things are separated by comma. If it is tab separated file, which is also called TSV, then all the values will be separated by a tab, and any new line means a new line, right? I mean, any break in line means that it's a new row, right? So an enter means a row, and whatever is your separator, either a comma, colon, semicolon, tab, space, then that would mean that distinguishes columns. Space is not a good separator most of the time. That's because some people have the habit of putting a space in the names of the column. So for example, instead of writing drug 1, we could write drug space 1, and if it was a space separated file, then it would become like a new column, right? So it's better to use something that is unique, that doesn't really exist. And commas are good because even if you have decimal numbers, there will be point something. So if it was like 3.1 or something like that, but generally you do not really save commas. Although I have had problems with this, because in some countries, instead of the decimal point, they use comma to denote a decimal point, like in Germany. So in Germany, like 3.1 is written as 3.1, and I don't know how it works in many other countries, but in some places the decimal is taken as a comma. So a tab separated version is sometimes even better, because generally you never have tab, right? So these are just different ways of storing files which are universal, so you don't need a special software to open it. So for example, if we open a Microsoft Excel file in a normal tab, in a normal text editor, this is what you see, right? Because Microsoft actually will puts a lot of comments and a lot of how do you say, style guide onto your data. So how to save it? So you see, it is not human readable. You will not see what the values of your file are, right? So this is an Excel file. This is .xls, but open in a normal text editor, and this is the main problem. Also, the problem with the Excel file is that sometimes it reformats your data. For example, it was a big thing. It's also published in, I think, PLOS Bioinformatics or something, that there is a gene name in human called SEPT9, SEPT9, and Excel always changes it to 9th of September, because it just reformats these things thinking that it's actually a date. And this gene called SEPT9 is one of the most commonly mistyped gene when people share their data as Excel as supplementary information. So Excel will do these kind of funny things without telling you sometimes. Whereas with the normal text editor, it never happens. They are universal, so you don't need special programs to read it. So that is the main advantage why most of the time bioinformatics are storing their data as CSV and not as XLS. Yeah. So of course you need to read these files and also write them. Yeah. So how, and then the sheets for XLS. So just to go through as an introduction, so you can make new sheets here, right? And you can also rename them. So if you click on the sheet and you say rename, then you can rename the sheet. So you can give it a custom name. And in R, you can either use the sheet number. So this will be the first sheet, second sheet, or the name of the sheet to include, just as Yura was showing to upload the sheet. Yeah. Just be very careful if you make an Excel sheet and you save it. No, in Excel format it's fine, but if you say save as, and then you say as a CSV format, then just be very careful. When Excel saves a file in CSV format, it only saves the first sheet. It ignores all the other sheets, so they are lost until and unless you also save it as an XLS file. Yeah. So when you are saving a file with Excel into CSV format, you have to save each and every sheet independently as a separate file. Yeah, so this is something that you have to keep in mind when you save things. Yeah. So just to show you, maybe we should have given this as an introduction, but anyhow, the two files that we have, we just made random files. It was not, I mean, we just made like an experiment that you might be interested in doing. So a control condition, drug condition, two drug conditions, and they are asymmetric in a way that you do not have equal number of counts or equal number of observations for each condition. So control has less observations, and you will see that what you will get is missing data, because when you upload this data into R, it's going to consider it as a table, right? So it will give you equal number of rows, but if something is missing, then it will just consider it as a missing data, right? And how to deal with that, how to make it tidy, how to remove this missing data, we can go on to it. So, but the first question is, was everybody able to locate their directory where the file was? First of all, I hope that you all downloaded the files, right, for the session. Then locate the directory, and then read the files. Yeah, so is there anybody who hasn't reached that stage? Because we can go over it a little bit quickly, but we can go over it one more time, and I'll change it now. Not change my screen to R. So just give me 1 second. So just to let you guys know, Yura is a bioinformatician from Cedric Blancpont's lab. And if you have any questions, you can also ask her. She's very good in all of these kind of things. Yeah. So, sorry. Yeah. So, one thing is that, as Yura said, that you have to be in the working directory, right? So you need to know which directory you are in, right? And as Yura said, you can actually set the directory as set WD, so set working directory, right? Or the other way of doing it, if you are not comfortable with that, is just to go to session and say set working directory. Yeah. So that is another way of going about it. So if you just go to session and say set working directory, choose directory, then you will be shown the directory. You will be shown a normal interface where you can choose which kind of directory you want. Right? So you should set your working directory as the directory that either has the files or somewhere where you know where the files are. So you can go, you have the path information. So the path is the location of your files, right? Because that is most important, right? Because if you cannot really specify the path of your files, if you cannot really specify the location of your files, then even R cannot find it, right? You have to know where your files are before telling it to R, right? And so either you can do it with session, set working directory, choose directory, or in R on the console with the set WD command. Either you can specify the directory, or you just say set WD round bracket, as Yura was saying, without any input, and you will find you will get a console, right? So the two packages that Yura said we will use is read Excel for reading Excel files and read R for reading R files, right? And from previous time, we will also be using dplyr to work with the files, and tidyr to make the files tidy. So we need all of these 4 libraries, so you can write them and get them so that they are ready, right? So let's start with the first file. So the first file just has 2 drugs. So it has a control and a drug, right? And it's an Excel file. So we are going to now only focus on Excel files, because although you can save your files as CSV, maybe most of you are actually saving it as Excel, right? So that's why we'll focus on Excel file, but you can do the same thing with CSV, so it's not very different. And as Yura was pointing out, the column names are what is also called header. So when you do read XLS or read underscore CSV, the column names are called headers. And if you have something with a row name, then you can specify the row name. And if you do not have a row name, then you can skip it, right? Most of the time when you have gene expression data files, you have a row name. And most of the time the row names are the gene names. But there are two issues, and we'll look at one of the issue today, not the second one. And the two issues are the column names have to be unique and row names have to be unique. So if you have a file that has gene names, but some of your gene names are repeated, then R will give you a warning and it will change the names which are repeated. So let's say if the gene, let's say ABC was repeated, then first time it will see ABC, it will keep it like that. The second time it will see, it will put it ABC.1. Yeah, so it will make a change because all the column names and row names have to be unique. And this is one of the reason why the tidyverse, so these packages that we use, doesn't really like the concept of row names, because they think that many of the times these things cannot be unique. And so if you specify or if you force them to be row names, then you can lose some information, right? Or you kind of mutate your information, you change it in a way that you don't really want to change things, right? So if you do save things with row name, just be careful that non-unique names are not allowed. You have to have unique names. And columns also should be unique, which is expected because each column is an observation, a feature. So there it's much more easy to have unique names, right? Yeah. So I hope that everybody can read this Excel files as Yura pointed out, right? Just go to the directory where you can point to R where the file is, and then use the simple function read XLS, part of read Excel package, and you only have to specify your path. That's it. Yeah. If somebody is still here who has not been able to read the file, just let me know. Yeah? So this way we will read the file, right? And also another thing is you don't need to specify the path. If you just say path equal to quotation mark, as Yura pointed out, then if you press tab, then it will show you all the files which are present in the directory, which is your working directory, right? So it will show all of this and it will show the directory structure as well. So there you can search for either you can search for the files or the directory where the files are. Yeah. So here, right? So we will read it and then we glimpse. So just like last time, glimpse gives us an idea of what is in the files. So we see that, okay, there are 3 columns. It says here 3 columns and a total of 13 rows, right? So there are maximum of 13 observations. Because the data is not tidy, so that means the same observation is separated on different columns. So because of this, we have some missing values, and these missing values are NA. So not applicable, or they're just called missing values. Yeah. So now how to make this tidy? So what we have right now is this kind of format. So our file was in this format on the left hand side, and we want it to go into the format right hand side in which all of our observations are in one column. Yeah. And the conditions in which these observations were made are in another column. So this becomes a feature, right? So there are there are many ways of doing it, but the tidyverse provides you 2 ways of doing it. And one of the ways is to use the function called glimpse. right? So, but we will not be going into Glimpse today. And the reason why we won't be going into Glimpse is because it's restricted, so it cannot do a lot of things. But you can have a look at it. So Glimpse is, sorry. So if you look at the help of Glimpse, then sorry, not Glimpse, sorry, Gather. My bad, I'm saying the wrong word. So gather, as the word says, it means to gather observations from multiple columns and to put them into one column, right? That is what the verb gather means. So as with the philosophy of tidyverse, any function should be a verb which should denote what it does. So the function gather, it gathers information from multiple rows, from multiple columns, put it into one column, right? That's what gather does. And this is part of the swirl exercise. So the exercise for this session will make you work with gather. Now, we will not be doing gather today because it's a completely developed function. They plan to make no changes to this function whatsoever. So it has been retired. Yeah, it says here life cycle retired. So it says development on gather is complete. And for new code, we recommend switching to pivot_longer. So that's why we will be using pivot_longer, because this is the new function that they recommend for using, and it's much more powerful. And we'll see how it is also more powerful. For the swirl exercises, you will be using gather, and gather will do the job for this file, but it will not do the job for the next file, and I'll tell you why there. Yeah, once we reach at that place. So how is the function pivot_longer working? So pivot_longer essentially means to make the file long, right? So when you gather all the observations, when you combine all the observations in one column, you're essentially making it longer. Yeah. So we want to pivot data from wide to long. Yeah. And it's still a maturing function, but it lengthens the data, increasing the number of rows and decreasing the number of columns, right? So it's very, very simple. So in this case that we have, we want to collect the data from all the columns and we want to combine them into a single column, right? It's as simple as that. So we have to specify a few attributes. So we have to specify the data. So here is the help page for pivot_longer. So we have to specify the data. We have to, of course, give it some data that it has to change. We have to specify the columns that we want to combine together, that we want to gather together, right? And then we have to specify the names too. So what will be the new name of the newly generated column that you will have, right? Because the call name, so control and drug, right? This is what was initially. So we had a column named control, a column named drug, and now that will become into a new column. So what will be the name of that column, and where will the values of the column that you want to combine, where should they go to? So what will be the name of that column? So that's it. So it's as simple as this. So instead of writing this in the format that is specified, where we have to provide data equal to data, we will use the pipe function, right? So pipe function will do the job for us for providing the data to this function pivot_longer, right? So we do not have to do it, right? So let's try it out. So first of all, the data that we got was in this variable xpay. Yeah. So we use the pipe function and we give our data to pivot_longer. So we don't have to specify the data. What is data? The pipe will do it. We have to specify the calls. Which column do we want to use? A nice helper function that tidyverse has given us is a function called everything. With this, you do not have to specify the columns. It means all the columns. Just take all the columns. Don't worry about which columns are needed. Yeah. Then names _2. Yeah. So what will be the name of the new column in which which will define the features, right? So we will say treatment, yeah? And then we will say values, right? So which column, the name of the column that will get the values, right? And once we do it, you will see that now it has put everything together. So this names _2 treatment. So now we have a new column called treatment that contains information that were previously the names of the columns, right? So it was control, drug 1, drug 2, control, drug 1, drug 2. Actually, now we are dealing with the file that has 3 drug conditions. It's fine. Yeah. It's both the same. It will work similarly if you have 2 conditions or 3 conditions. It doesn't matter, right? As long as you want all the columns, you just have to specify everything, right? And the values will go into a column called cell. Yeah. And what you see is that it has shuffled it a bit, right? But that's okay, because first thing, it has shuffled it a bit, and second thing, what you will see is if I print a bit more, so if I try to print everything, you will see that it will also keep the missing values. So here are the missing values, right? So we want to remove the missing values, and we want to arrange the column a little bit, right? And both of these are fairly straightforward. If you see here, it will tell you values _drop _NA. So if there are missing values, should it keep those values or should it drop them? So by default, it is false because it doesn't really want to drop anything. You have to specify, right? So very simply, within this function pivot _longer, we specify this as true. Yes. So please drop the values which are missing, right? And then we again print n equals to 40. And now you will see that there are no missing values. Right? The data is tidy because all the values have now become one long column, right? All the conditions have also become one long column, right? And without any missing values. Yeah. But now, we don't really want to see it like this. Control, drug 1, drug 2. We want to look at it in a better way. And if you remember, then to arrange a column, the verb is arrange, right? So we will say that we want to arrange our column, which is called treatment, right? And this should arrange the column called treatment alphabetically, right? If it was a number, then it would do it numerically, but here it's alphabet, so it would arrange it alphabetically. And then all of our control observations come together, all the values come together, and the drug 1 is after that, and then after that will be drug 2. Okay. So print n equals to 40. So as you can see now, the data is nice, the data is tidy, and they're all arranged well, right? And this thing, you can finally save it. You can overwrite the same variable, that's okay. Or you can save it into a new variable. So we can say xpay.tidy, okay, just to specify that it's a tidy variable. And to save it, you have to give it the assignment operator. This is when you want to pass the data to a function, specifying that the function should use that data as an argument. But when you want to save it into a new variable, you have to use the assignment operator, right? And now it will not print anything. But when we look at this data, we see that it's now tidy. Yeah. So it has exactly the same kind of data that we started with. So we read the data from an Excel file, and then we made it tidy. Yeah. And we made it tidy just with this one function, in which we said that we want all the columns to be combined into one single column, right? So just as an example, what if you did not want to combine all the columns into one column? So just as an example, if you wanted to, let's say, leave out, we'll go into more detail as the second one, but just to tell you how to do that. What you can do is just specify as negative subsetting. So if you say minus, and if you say, let's say drug 1, and what it will tell it is that combine all the columns which are not drug 1 into a single column and just leave this column as it is. Yeah. So you see it left the column drug 1 here, and this is a wrong example to give because here all the data is combined, has to be combined together, but we will come to another example. Yeah. So if you specify everything, then all the columns are combined into a single one. If you specify or you can specify the names of the columns that you want to combine, or you can do negative subsetting. So you can tell drop this column, combine everything else. Yeah. So now we have our data xpay.tidy, which is tidy, and because it's tidy, we can do any kind of statistical analysis. We can do plotting with it. It will work really fast, right? So just let me know in the comment section if this is clear, because this is an important point which you will need to master to get your data into a place where it's then usable in R with the formula function and everything, right? So if it's clear, then we'll go and then we can make a few other statistics. Yeah. Okay, so we can just make a small revision of the next time. So how to get some kind of summary statistics from last time. So let's say if we wanted to get the average, the mean cells for each group, right? So now we have it tidy. So we can say group by treatment, right? So we wanted to group. I could not save it as an object. No, you can save it as an object. So all you will have to do is to just do write underscore CSV, and you just have to specify x equal to xpay.tidy, right? And the path. So whatever the path is. So a path will be a new file. So let's say experiment underscore tidy.csv. As Yura said, it's a bit difficult to save files into Excel format from R. It's easier to read them. So that's why we only restrict to CSV. What you can do is if you really want Excel file, save it as a CSV, open the CSV file in Microsoft Excel and then save as Excel. And that's what I also do because that's the easiest actually. Yeah. So if we say list.files, okay, there are too many files, but experiment underscore tidy.csv, so it was saved. Adria, do you mean your the tidy object? You'll have to use the assignment operator. So the assignment operator and then into a variable. So after you have done all the things, then you have to use the assignment operator. Okay, just try it again and just try to put it with this assignment operator and into a name xpay.tidy. Or if you have an error, just type it out. Yeah. Okay, so we'll try to do some statistical analysis. So let's say if you want to do, we want to find the mean, right? Right. And we want to find it for each group. So first we say that we want to group it, and then we say that we want to call a summarize function, right? So summarize function will allow you to make a summary. Yes, Adria, you have to not put the pipe. You remove the pipe, just put the assignment. Yeah. So we have to call a summarize operation, and then within the summarize operation, what we give it, we give a function, right? which will be called by for each group, right? So let's say if we want to find the average, then we can say mean dot cells equal to mean. So mean is a function, and what R will do is it will calculate the average for each group and then make a nice table in which mean dot cells is the name of the column, and it will be split for mean of cells, right? So we have to say that which column mean do we want, right? So mean, we want the mean for the column cells, but they have to be split by treatment, right? So this is split, apply, combine, right? So we split our data by treatment, we apply the mean function, and then we combine them into a nice format which will give us the data, right? So this shows that the mean of the cells for the control group is this much, for the drug 1 is this much, for the drug 2 is this much. Yeah. Similarly, you can do standard deviation. So let's say if we want to have let's say if we want to have mean of cells, and along with that we want to have standard deviation for cells. So we say standard deviation for the column cells, right? So standard deviation bracket cells means for the column cells I want standard deviation, and group by will specify that it should split the data by the column treatment, right? And in this case we get the mean and we get the standard deviation, right? So we have taken the data from Excel sheet, we got them into R, made it into Tiny, and then we can use the power of tidyverse to get these kind of aggregate statistics. But what if there is a kind of mathematical operation that you want to do which is not present in R? Most of the time it will be present. If you Google it, there will be a package that will have a mathematical operation that you want to do for sure, because that's what R is for. It's for data analysis, so people have made it. But let's say that there is one. So let's say we want to make standard error of mean. Yeah. So standard error of mean is equal to standard deviation divided by number of observations, right? So we want to have this number, right? So how will we go about getting this sort of number? Yeah. So if you want, you can pause and try it as an exercise. I'll just specify one thing to get the number of observations. So how many observations were present for each group? There is a helper function for summarize, which is just called n. So if you say number dot cells equals to n, so n is the helper function, and what n does, it gives you the number of observations, so the number of samples, right? It just helps you to know how many there were present. Sorry, it has to be cells. Yeah, sorry, I think for n, my mistake. For n, we do not really have to give, we cannot really specify a column, because that argument is coming from grouping, right? Because what n is telling us, what is the number of observations per group, right? So that that information is not coming from the column cells, it's actually coming from the column treatment. So there should be no argument in this. As long as you have done a grouping, there has to be no argument for n. Yeah. So what this n is a helper function for summarize, and it will give you the number of samples in each group, right? So this tells us that there are 7 samples in the control group, 10 samples in the drug 1 group, 13 samples in drug 2 group. And of course, this information doesn't come from the column cells, which has the number of cells, right? But it comes from this grouping. Yeah. So this is the number of cells. And now let's say we save it, right? So there is no pipe now, just an assignment. So we save it as xpay.stats. Yeah. And now based on this information, let's say we want to make a standard error of mean. So standard error of mean means that we want to divide standard deviation by number of cells, right? So anytime we need some information that is a combination of the columns, tidyverse allows the verb mutate, right? So mutate means you want to change, you want to do an operation on the columns, or you want to combine the columns in some way. Essentially, you want to add new information, right, which is already present, right? So we just say xpay.stats mutate, and then sem.cells equal to mean, sorry, not mean, standard deviation dot cell divided by number dot cells. Actually, it would have been better to name this column as number dot treatment, right? Because these are the number of samples per treatment. Number dot cells kind of makes it a bit misleading. So if you want to change it, then you can change it. Yeah, you just have to go here, back here, because it's kind of a bit misleading. It's not the number of cells, but it's actually the number of samples in each treatment, right? So now we get our SEM, standard error of mean, right? So this operation, there is actually, I do not think that there is yes, there is. I do not think that there is a inbuilt function that will calculate standard error of mean, but using this, you could do this, right? But what if you really wanted to calculate standard error of mean many times? Like, like for all data sets that you have, you really want to calculate your standard error of mean. So it's not an operation that you want to do sometimes, you want to do it for everything, right? So you want to make it a bit more faster. Yeah, so you don't want to do all of these steps where you actually calculate the standard deviation, you calculate the number, and then you divide them. I mean, it's possible, but a bit tedious to do it over and over again, right? So what you could do is you could define your own function. So this is the first time that we will be defining. Yes, my mistake. It is the square root. Thank you for catching that. SQRT. So Vivian pointed out that the standard error of mean is not division by number of cells, but actually it's by the square root of n. Yeah, so we will have to just put a function square root. So square root is a predefined function in R, right? So then, but anyhow, so what if we want to do this standard error of mean many times, and we want to kind of automate it? So we will write our own custom function today. So this is, so until now we were making our own custom data and we were changing the data, but how do we write a new function? Yeah, so we will do that now. So the best is to start a new R file. So just say file, new file R script. Yeah, or the shortcut is Command Shift N. So that will give you a new file. Yeah, and we will define a new function called SEM. So whenever you want a new function to be defined, right? So what is a function? So a function is something that will take an input and give you an output. So what we want is, we want to take an input of numbers, we want to take a group of numbers, and we want to give back the SEM, right, directly from the numbers. And in between we will do the calculations of standard deviation and length, but finally we want the SEM directly, right? So when you want to define a new function, you say name, the name that you want to give to the function, the assignment operator, then function. So this tells R that what you are defining is not a new variable, but a new function. And what I just said is a little bit of a lie, because R treats functions as also variables, but just in your mind, they are a special kind of variable. So they are something that can take an input and give you back an output. Yeah. So they can do operations. Yeah. And then just like any other function within the round brackets, you have to specify what kind of data you will get, whether it is a data that you want to get, or it is a data that you want to specify by default, right? So let's say we will keep data empty. So this would mean that we need some data, right? This function will not work without any data. And let's just make multiply. So we can make multiply by 1. So that means that if somebody wants just SCM, then they leave it as default. But if somebody wants twice of SCM, then they can specify multiply equal to 2, and then our result that comes back is twice of SCM, right? So just make a new function, right? So sorry, this we have to specify for SCM, but I will just write here arguments, and then in curly bracket we will say what kind of operations happen inside of this function, right? This is just the way to define a new function. And last and not the least, we have to specify a return command. So what will be returned from the function, right? So now let us write one function for SCM. So we will name the function SCM, right? So it will give us the standard error of mean, and it is a function, right? Its arguments are data and multiply equal to 1. So how do we calculate the standard deviation? So first we just say standard deviation dot data equal to SD of data, right? So right now the data is not really specified. We are writing it for a general data that we will provide when we call this function, right? So there is nothing like data. Data will be given by the user or by you when you call this function, right? And based on that data, we will calculate the standard deviation by calling the function standard deviation, right? And then we want the number of samples in our data. And because SCM we will calculate based on a vector of number, so on a numerical vector, right? So we hope that the person who calls this function passes a numerical vector to this, right? So for numerical vector to get the number of samples, we can call length, right? So length of data, right? So let's say if somebody passes 4 numbers, so length of that vector of 4 numbers will be 4, right? Yeah. And then the SCM of the data will be standard deviation of the data divided by square root of the number of samples. Okay. So now we have calculated the SCM based on the input of data, and this is what we want to return. We want to give back this information, and we have to say SCM.data. So this variable that this function will calculate in the background from this input data, we will return. And this is the only way of defining a data in R. This is the standard. This is the only way actually. So there is no new package that makes it different or anything like that. So it's always like that. Yeah. The name of the function, then you tell R that it is a function. It's not a variable. Yeah. You specify the arguments. Some you can leave. The arguments that you leave, the user has to provide. Some arguments you can provide a default value, right? And then you do some calculations. The result of the calculation you return. Actually, what we want to do is we want to say SCM dot. We not only want to return SCM dot data, but we want to also multiply it by this variable called multiply, which will be 1. But if user want, they can do 2. So then it will be twice of SCM, right? And then we save this file. So just say either command S or file save. Yeah. So you save this file, and I will just call it SCM .r. So because it's an R file, you can call it SCM.r. Right. So we save this file. Now there are 2 ways of calling this function. One thing is you can just come to any part of this function and say run. And when you will say run, what you will see is that it actually doesn't run anything. R doesn't run anything, but in the environment, you get a new function which you have defined, right? So now a new function has come, which is called SCM. And all of the libraries and packages that you see are essentially just a collection of such kind of functions that people have made, and they provide it together as a package. So that's what a package is. So when you install these libraries, they are exactly these kind of functions that people have defined to do different operations, right? And this is your first custom function, a function that you create, and you can create any kind of function that you want. As long as you know what you want what you want to map from input to output, you can make a function out of it, right? So let's try it. Yeah. So all you had to do was go to any part of this file, just say run. It should come in the environment as a new function. And now let's see. So let's find the SCM of let's say 1 to 10, right? So SCM, and we pass it a numerical vector, which is a combination of 1 to 10. Okay, so the SCM is 0.957. Let's see, let's test if this is true. So we will have to calculate the standard deviation of 1 to 10, and then we divide this by square root of 10, right? And it gives us yes, there is no custom function SCM. I think there is a, so Vivian asked, is there no custom function SCM? I believe there is not in a base R, but I think there are some statistical packages which you can install, which will give you all of these functions. Yeah, but it's super simple to have your own, and I would actually recommend making your own function. Why not? Right. So this was the way to make your own custom function, right? So now you never have to make this calculation. As long as you want SCM, you just call this function. And let's say if you want twice of SCM, then we also made another parameter, multiply by 2, and we'll get this number multiplied by 2, right? This is one way of doing it. And the other way of doing of calling the function is that I'm going to remove this function from my environment. So I'm going to say remove SCM. And the better way to do this is to use a source. So what source means is, source means that it is going to read an R file that is full of functions, and it's going to put all the functions into your environment. So it's the local way of saying library. So when you install a package, then it puts it into your global environment, and then you say library, that package name, and it gets all of the functions. I mean, it doesn't get the functions in your environment, but it gets them in the global view, right? So then you can call the functions, right? So whenever you want now to use your SCM function, and what you can also do is you can keep adding more and more functions. So it's things that you keep on using a lot of times, you just keep on adding to this one file. And when you want to make a calculation, just say source apostrophe and the name of this R file, scm.r. And when you do this source, you see the SCM function has again come back into your environment. And now again, you can call the SCM function, right? So this is very common, and I typically do this. So if there are some things that I want to automate, and they are not really present in R, but you kind of use them a lot, especially related to data cleaning, then instead of typing 10 commands every time that you want to do it, just make a new function, save it, and just source it, right? So you get all of these functions together. Yeah. So now let's make the SCM of our data set. Yeah. So initially we did make an SCM, and it was like here. Yeah. So you see, we had to go through all of these steps to get the SCM, but now we have a function for standard error of mean. Let's do this. So we have an xp.tidy, and all we are interested is in standard error of mean. We are not interested in any other value, right? So all we say is group by treatment, And then we want to summarize. We want to summarize our values into something. So we call summarize function, and we say sem dot cells equal to our function sem, right, which we have defined, and the argument that we give will come from the column cells, right? And here you go. So you get the exact same results: 0.508, 0.650, 0.654, 0.508, 650, 654, right? Without having to go through all of those steps. Yeah, you have automated it. So you have made an automation on SEM, on standard error of mean, right? Yeah. So this was how to make your own function, how to make your own operation. Yeah. So just to do it one more time, we'll practice it once more. So as a practice, let's define a coefficient of variation. Yeah. So coefficient of variation, if I'm not wrong, I may be wrong, is I think standard deviation divided by mean. Yeah. So that's the coefficient of variation, right? Because essentially, if your mean is very high, then your standard deviation can also be very high. But if you want to compare two populations, how much distributed there are, then a better is to compare coefficient of variation, in which you normalize your standard deviation by your mean, right? So it's standard deviation by the mean divided by mean, right? So the one way to do it would be to go step by step, right? To first calculate the mean, to first calculate the standard deviation, and then to take a division of the two. So let's do that. At least let's do it first. So we will say mean dot cells equal to mean. So make a mean value, get the information from this column cells, and store it into a column whose name will be mean dot cells. Right? And then we will make a standard deviation. Right? And then we will use this data to make a new column, right? So because we want to make a new column that is a combination of these two, we use the function mutate. And in this way, coefficient of variation on cells equals to mean dot cells divided by standard deviation dot cell, right? So is this clear? I hope that this is pretty standard now. I mean, this is the dplyr, the tidyverse way of finding coefficient of variation. So first we group our data based on treatment, then we calculate summary statistics, and then based on the statistics that we calculated, we make a new operation in which we make a division. Okay. And here now we get the coefficient of variation. Okay. Now let's do this via function. So we should define a new function which is called coefficient of variation. And just in this case, I'm going to put this in the same file, sem.r. But a good practice is to rename this file as myfunctions.r and to source it every time that you need it. And then in the file myfunctions.r, you can have a collection of, let's say, 30, 40 of your favorite functions, right? The functions that you want, right? So we will say that coefficient of variation. So I hope that this my definition is correct, right? Standard deviation divided by mean. Yeah. Okay. So we'll say that coefficient of variation, we name this function as CV, and this is a function. It's not it is a variable, but it's a variable which is a function, right? And it is going to take data. It's going to take some data. Okay. And then we are going to calculate the standard deviation on this data. We are going to calculate the mean on this data. And then we are going to calculate the coefficient of variation on this data. So we'll do standard deviation dot data divided by mean Yeah. So these are all the operations that we want to happen from input to output, right? This is the transformation. And once we are happy that this is exactly the transformation that we need, we can say return cv.data. So every time that you call this function with an argument data, it will give you back the coefficient of variation, right? We save this file, which is scm.r, and again we go and source this file, right? So I mean the file name doesn't really matter. Whatever functions you have defined inside the file, it will source all of them individually, one by one, right? So now when we source it, we see that we got a new function called cv in our environment along with scm, right? Just later onwards, if you are really interested in these, I would strongly recommend you to make a collection of your favorite functions. Just name this file as my functions, or if you want to be even more specific, you can say my statistical operations, and you can differentiate your own functions, right? So now let us make the coefficient of variation, but in a bit more direct manner. So we can leave all of this and we just say cv cells, right? So we take our data, we split it based on different treatments, so which is group by, and then we call the summarize operation, in which we will get the output of the function cv on the column cells. Oh wait, did I make a mistake ahead? Yeah. Okay, that's why somebody commented. So initially I had made a mistake, so it is opposite, so standard deviation divided by mean. This is another problem that can happen, because once you define your own custom function and you run it through a few positive control, let's say, like you go and calculate the coefficient of variation using some other tool, and you test your own custom functions, and then you do not play around with it, there is much less error that can happen. Because now if we know that this function called cv is working and it's going to give the coefficient of variation, such mistype, mean divided by standard deviation instead of standard deviation divided by mean, it cannot really happen, right? Because now we are not going to be typing these kind of things. It's done in the background. Yeah. So now these numbers are matching, right? So the defining these kind of custom functions help with automation. They make your code cleaner, and they do avoid errors, so you are much less prone to errors. But again, when you define a new function, run them through a few controls. So take a few numbers, get some analysis done, and compare it using some other tool. So yeah. Okay, so this was how to define new functions, new things. So with this, now you can calculate standard error of mean, you can calculate coefficient of variation, right? So now we can go forward. If there is any question or issues, just ask. But getting your data into R and defining custom functions, these are two skills that you would need once you get to some kind of data analysis and you want to do it quick without much error, all of these kind of things. Yeah. So now we go to the next Excel file, and the next Excel file we have half an hour. Okay, so that's good, because the next Excel file is a little bit different from the previous Excel file. So we will read it. Yeah. So again, I'll go through this a bit again. So first, to read the file, you have to know where the file is, first thing. And second thing, you have to point R in the correct direction. Yeah, R cannot really guess. There is no search function. I mean, there is a search function, but it's not going to search your whole directory, right? So to make sure that R knows where the file is, you have to set your working directory. using session set working directory or using the command set wd. You can either set your directory like this, yeah, or you can also check what is your working directory, but by just saying set wd round brackets. Wait, this was the command, right? Sorry, no, my mistake. It's get wd. So get working directory. It's not set wd. So get wd means get my working directory. So right now this is the current directory, right? So if you want to read a file from your working directory, you have to know how to reach to that directory. That is something that you have to put into R, right? And also what kind of file it is. So beforehand, you should know if it's a comma separated file, tab separated file, Excel sheet. And if it's an Excel sheet, then which sheet do you want? The first one is by default, but if you want others, then you have to specify that, right? So the experiment with the right, so we will read the other file. So we will call it, let's just call it experiment, and we will read using read xls, and our path is, so we will read the file experiment with features, this file, and we'll just focus on the first sheet, right? So let's view this, the contents of the file. So we read the file experiment with features, not experiment 2 drugs. I think we are done with the experiment 2 drugs. That was all that we wanted to do. Now we will move on to experiment with features. Yeah, and save the result of this read xls into a variable. You can call it anything. I'm calling it experiment, right? And here is how this file differs from the previous one. It has linked data, and when you have linked data, then gather, which is the command that we did not discuss today, it has problems. So what do I mean by linked data? So each sample, for each sample, there are 3 observations. Actually, there are 4 observations. So the first observation is how many cells there were, yeah, upon this kind of treatment, upon the control treatment or upon drug treatment. So how many cells did we either see or anything, yeah? Then what was the age of the sample? What was the gender of the animal? So was it a male, female, right? So these additional parameters we have added, and they are not independent parameters. They are all linked. So it is this same sample, the first sample, which had 3 cells, which was a female of age 32, right? So we cannot really shuffle them around. So they have to stay linked at all time. And similarly for drug, so there is one drug treatment, and again 3 parameters, and then a 4th parameter, which is common, which was the day of collection. So these 2 samples were collected on Monday, then these 4 were collected on Tuesday, then these 4 were collected on Wednesday. And as you see that on Wednesday, there was only 1 sample that came from drug, but 4 came from, 1 that came from control, but 4 that came from drug, right? So this is a linked data set, right? And we have to respect this kind of linkage, right? So at the end of the day, when you get a tidy data set, it should have 4 columns because there were 4 features. It should have 5 columns because there were 5 different quantities or attributes or features that were measured. First was whether the sample came from control or drug, right? So that's the first feature. What was the treatment? The second feature was the cells. Third was age. Fourth was gender. And the 5th feature was the day of collection, right? So at the end of the day, you should end up with 5 columns. And if you do that, then you have what is called the tidy data set, right? So let's see how to make them. and the gather function will not work here. Only pivot.long function will work here, and that's why today we only discuss pivot.long. But in the swirl exercise for this session, you will look at gather. Yeah. So we have to get this data set into it, but we cannot just say that get all the columns. So we cannot say everything, right? Because it's linked, and we have to respect the linkage. So what pivot.long allows you to do, and this is what makes it very, very powerful, is that it allows you to tell, based on the name of the columns, how should it separate the columns or how should it combine the columns. So in this case, you see that after the underscore is our before the underscore is a feature, right? So all of the columns which have the same value before the underscore, so like this column cells and this column cells, so they both have the same value before the underscore, they should be combined with each other. And then these two columns should be combined with each other because they have the same name before the underscore. So age, so they should be combined, and then gender and gender should be combined, right? So this is a critical information. This is this is the information that will allow pivot.long to automatically combine the data set, right? This kind of information. And we'll go through another example in which you do not have this kind of naming. Yeah. Honestly, if you do not name, I mean, if you get some data set which is not named like this, which allows you to at least get some sense of how to combine the data, then better ask the person to annotate the data a bit better. Yeah. Anyhow, and then your treatment is defined by what is after the underscore, right? So at least here the column names are pretty sensible. Yeah. So once we have this kind of sensible column names, it's very, very easy to do. And another thing is we should not combine the data set day because it's only one, right? So in this case, this is something that is already in long format, right? It's already in long format because all the observations regarding day are in one column. So this is already tidy. The first three columns are not tidy, right? So now we combine it. So we take pivot.long. Okay, I'll do it here because it's a bit more center of the screen, so it's a bit more easier to see. So first we have our data set called experiment, right? Let's just check it again. This is our data set, some missing values, everything, it's okay. So we pass this to pivot.long. So we don't need to specify the data because the pipe function will do it for us. But we do need to specify which columns. So we just say that we want to combine all the columns except day. So negative subsetting, right? Minus day. Okay. And then we have to specify the names and the values, right? And here there is a very nice trick that this function allows, is that it allows you to extract the names of the column from such sort of structure. So what we will say is, you can also look in the help page, they also define how to do it. So names.to. So in the name of the columns, there are two you have to tell it to split the name into two places, in which the first place will define the value, right? So that means that this number here is the value of cells. This number here is the value of age. This female here is the value for gender. Yeah. So the first thing before the separator defines what kind of value is in the column, right? So this column has the value for cells, for age, for gender, right? So to do that, we just say dot value and in quotation mark, right? So this is just a helper function which will tell this function pivot.longer to look at the name of the column and to divide the data in a way in which whatever is before, whatever is the name is the value, yeah, and after that, so whatever is after the underscore is a treatment. So this is the thing. Right? So that would mean that it will make a new column called treatment, in which it will put control or drug in that column. Yeah. So what was the kind of treatment? Yeah. So dot value means that whatever is before the underscore, whatever is before a separator defines the value. Whatever is after defines a new column, right? And you can also do it iteratively, yeah, because if you have value, then something, then you can just keep on doing it more and more, yeah. And one more thing that we have to define is the separator, just like we had to do with CSV. So we have to say that these two things, the value and the information about a new column, is separated by an underscore. Yeah. And that is it. This is it. Now it will keep the linkages. It will respect the linkage. Yeah. So what it will do is it will look at the name of the column and it will see that these two columns have the same characteristics before the underscore, and it's going to join these two. It's going to join these two. It's going to join these two. And then it sees that after the underscore, there are two characteristics, control and drug, and it's going to make a new column called treatment, in which it is going to put that information. Okay, where did I go wrong? Sorry, my mistake. This is a vector, not two columns. Yeah, of course it has to be a vector, right? Because it has to be a combination. Yeah, because it's a single name, right? So if it's a single name, it means that it's a combination of value underscore treatment. Yeah, it's not two different things. Yeah. So my mistake. So if you type two brackets, just change it, because the name of a column is a single character. It's a single vector, right? And so it has to be a combination, right? So the name is a combination of value and treatment separated by underscore. Yeah. And you will get your data as tidy. So it will not do anything today. It will repeat it, right? Because it has to be repeated, because now control and drug will become duplicate, right? So it will be repeated, but all the collections are together, right? So these things are together, and now it's tidy because all the information about cells is in one column, all the information about age is in one column, gender, treatment, and day, right? So there is no information that's split. So this is a very strong function to make your data tidy, and this is kind of like a way of telling it which ones to combine and which ones to not combine, and how to combine. So you just have to get familiar with this notation and use it, right? So it just tells the function to look at the name of the column and to get that information from the name of the column. Yeah. And of course, we do not want missing values. So either we can here itself specify to drop the non-existing values, or we can go to a function called drop underscore NA. So anytime that you want to drop from your data frame all the non-existing values, you can call this function. It's a function that will take any data set as input, and whatever is missing, it will drop all the rows. So now we will get a clean data. It's not completely clean, right? Because it's a bit shuffled. So we can just say arrange treatment. And now the data will be clean. And this is the perfect format. right? So now we have the day, we have the treatment, cells, age, gender. Right? If people want me to go over this again, I can, because we have 15 more minutes and actually not much more to do. But this is the most important thing. Yeah. Otherwise, I'll just show you what to do if the column names are not like that. Essentially, the solution, if the column names is not like this, is to rename the columns. And there is a function called rename which will rename the name of the columns. So we can go through that. Yeah. So let's read the sheet number 2 from the same Excel, because it has very bad names, and you will see that now. So if we want to read sheet number 2, we use exactly the same function, but we just say sheet equal to 2, right? And you see that in this, if you also open this Excel file in Microsoft Excel, then you will see that I don't get why we put the dot in value. The dot in value specifies to it, it specifies to the function that to replace this string by whatever is here, right? Because when we say treatment, then it will name the column as treatment, right? So this is the name of the column that we got the name of the column as treatment. But here dot value means that it is going to set the name or the value of the column, so the value of the name of the column, based on what it finds here. So it makes it a bit more generic. So it not only combines columns that have the same name, so as they will have the same kind of value, but also the name of the column it will get from here, right? So we don't specify what the names of that column will be, that this function will do it automatically. Yeah, so that is why it's dot value. So dot means replace. Dot generally means that it's going to be finally a string. It's going to be finally a character string, but instead of us giving us the value, it has to extract the value. That's why it's dot. Yeah. Right. If we did not say it, then it would just let's see. Actually, I never really tried it. What it would do, because it's going to it's going to say that it cannot really combine things, because it cannot really find something that is common, right? It has problems finding things because it gets conflicts, right? Yeah. So in this other file with improper naming of columns, first of all, there is a column that is just called age. So it doesn't really say whether it is the age of the control sample, whether it's age of the drug sample, nothing. Yeah, so it just says age, and then it also just says gender, and it repeats this thing twice, and it repeats also gender twice. And because column names and row names have to be unique, so when this data is imported into R, R is going to add a few things to it. So it adds the position of the column. So it makes age dot 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 2 and gender dot 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 3, right? To be very, very honest, this is badly annotated data because it's highly susceptible to confusion. I mean, if you just say age and you are noting age of multiple groups, well, then at least you have to specify which group does the age belong to, right? Because if somebody just mixes up the data, then there is no way of going back, right? So it has to be age of control or age dot control, age underscore control. I mean, something like that has to be there, right? But anyway, if this is the case, it's still fine because we can rename the columns. So it is going to be a bit of a pain. And to be very honest with you, cleaning the data and getting it into a tidy format uh, is, I would say, around 20 to 50% of the work. Because once the data is in tidy format, things go very fast, because analysis is pretty quick, plotting is pretty quick. um, but getting things to tidy format is half the work many of the times. And uh, that's why there are so many packages that help you do that. Yeah, I mean, the whole tidyverse was made to help you make these kind of things. So we'll just say rename. So your data will be experiment 2, right? And unfortunately, then you just rename all the columns one by one, right? Either you can rename all the columns one by one, or you can pass a string, a single string, giving you the column names of the columns. But in this case, so first, what is the new name that you want, and then what is the current name? So we will have to say cells dot control equal to control. Yeah. So age dot control. So I'm going to put a dot now to show that it's also going to work with dots. It doesn't need dashes. Yeah. But this is, yeah, there are ways around it. But I find that if your data is not too big, then just doing this is fine. So dot drug. A bit boring and tedious, but yeah. Or you can directly go to Excel and then save your, change your column names there. Yeah. And once you do this, yeah, you get new column names which are now compatible with making it tidy with this function pivot underscore longer. This was also to show that sometimes coding is tedious. Yeah, it's not always very elegant, and there are solutions which will also work with this kind of data. So it's not like it's not possible. But the thing is, then you have to learn a new package, and you have to learn just one new function just so that you could do it, like you could work with this. Uh, I find that it's better to get expertise in one function and to really know how to work with it, and then to try to force get the data into a better format, right? So now we can make it into a pivot underscore longer, right? We don't try to provide the data, we just have the pipe, but we need to provide call. So we again say don't do anything to the column day because it's already tidy. And the names are, the names of the column is a combination of the value and a new column called treatment. And the separator this time is a dot. Okay, I think I made a mistake somewhere. Sorry, it's names dot separator. Separator. No. Okay, let me just see why is. Does it not work with? Okay, with underscore it is working. I'm not really sure why it doesn't really work with the dot. So I guess that is, maybe I made a mistake in the typing. So just have a look if it works for you guys. Yeah. Yeah, I'll try it again. No, it says that there is some error. Okay, we'll see if there is a problem with the dot, but the underscore is for sure working. I was trying it with a dot, so I guess the underscore is the best. Yeah. Now let us see. Okay, yeah, so there is a problem. There is the 4 missing. Yeah, there was some problem with underscore. It is working, right? Yeah. Anyhow, I hope that this thing is happening on all the computers, on everybody. With it's possible to do this kind of sorting. Yeah. And then we can arrange our data. Right. Okay, so we have been able to get our data into R. We have been able to make it tidy, and also to get it into a format where it's ready for analysis. But do you have to do this all the time? It seems tedious, no? I mean, it seems like if you really need to type all of this again and again and again, then it can become quite boring, right? I mean, or you need to remember how to do it and all of that kind of thing. So is there a way to save the data without being in a CSV format? I mean, not with a file, not with a single file. You can of course save it with write.csv. Yeah, this is no problem, just like Yura was saying. So you can save the new tidy data as write.csv, and this will save a new file. But there are better ways to save, and the best way is actually to save it as an RDS object, because this is very less memory, so it's sort of like zipped. Yeah, and then anytime you call, you read this object, you get your data back exactly in the way in which you saved it. So you do not have to do any kind of processing, nothing. You save it as an R object and you get back an R object. Yeah, so this is something good. So let's say now you have made your data tidy, and now you are happy with it. You want to save it for later. So we just do save RDS. Yeah, and then which data do you want to save? So we will say experiment 2. This is the data. This is the R object we want to save. And which file do you want to save it as? So we'll specify it completely. So when you want to specify a file, make the quotation marks. Okay? And when you press tab, then that will be the folder in which the file will be saved. So if you want to change the folder in which the file will be saved, then you can say change the folder. Okay? So let's save it here, and we have to specify a new file. Just be careful. If you specify the same name as a file that exists, then it will be overwritten. R doesn't tell you any kind of warning or anything, so it will overwrite the file. Yeah. So let's say we want to call it experiment dot underscore tidy dot RDS. So you don't need to specify dot RDS but it's an RDS file. So RDS stands for R data structure. Yeah, so it's a way for saving our data objects, right? So just so that you know later onwards that what you have saved was an object, right? And now once you do it, it will save it. Now let us try to read it. So first thing I will do is I will remove this object from my environment. So to remove an object, we can use remove. And if we want to remove everything, then it's remove list equal to ls. So this will remove everything that is in my environment. If you don't want to type it, just go to the help page of remove, question mark remove, and it will show you how to remove everything. So it says at the end here, if you want to remove everything, rm list equal to ls or remove list equal to ls. Okay. It will clear out everything that is in your environment right now. So now the environment becomes empty. If you have very big data frames and you have made them into tidy format, then it's better to remove the old one because it cleans up some memory. Yeah. And then to just keep the tidy one. You can always go back. Right. So now let us read this data frame. So if we say read RDS, so read an R data structure, and we'll save it into a new experiment, right? Because it will read it, but if you do not save it into a variable, then it will just read it, right? You have to save the result of the function into something, right? And then we say file. We go to the and we get this exact same object back, right? So now we do not have to worry about making it tidy again. It will have absolutely everything in the way where you saved it. So it will have all the name of the columns, all the structure, everything will be defined. It's not because sometimes you might have defined something as a factor, you might have done some operations, and if you save it as a CSV, you will lose all that information. And if you don't want to lose all that information, then you can save it as an R data structure. Yeah. And this is a bit more faster, so you can pick up your analysis exactly at the place where you left it. You can even do this for plots. So next week on Wednesday we will be making plots, so you can even save a plot object and then come back to it later. You can save it to analysis. So let's say if you made an ANOVA model, you can save the ANOVA model. So it's not necessarily that you save a variable, you can save anything like this, right? So so let's just with one last thing, let's just run a quick ANOVA model to see if cells are changing with treatment. And I just want to show this because this is something that this last thing for today. So to make the ANOVA model, if you remember, we have to call AOV, right? And so we say, so I'll just glimpse at the cell. It's not really. Yeah. So it was not tidy. I saved a non-tidy one, but we can make it tidy very quickly. So if we call an ANOVA model versus treatment, the data is coming from experiment. So what this will do is it will compare different kind of treatments. It will group the cells. It will split the cells based on different kind of treatments, and it will make an ANOVA model. So what I learned last while searching for this is that you can make multiple models. So let's say you are interested in a covariate. So let's say you think that it's not just the treatment that is having an impact on the number of cells, I mean, some observation that you make, but it's also a combination of treatment and age, right? So here we have the treatment, but also the age. So maybe there is it's a covariate. The impact is because of treatment, but also because of age. How to judge this is that you make a new model in which we make treatment plus age. And this means that now it will model the cell number as a combination of treatment and age, right? And what you might also think that it's not just treatment and age that is having an effect directly on cells, but maybe age is having an effect on treatment or vice versa. So let's say in your control group, there were younger people or younger samples than in the other group, right? So these two are interacting with each other. So they are not independent variables, but they are interacting with each other. And if you want to see interactions, we say multiply. So this means that age or treatment may have an impact on each other, and this together can also have an impact on cells, or whatever you want to observe, right? So this is your observation, and these are the things that can have an impact, right? So we can make these 3 ANOVA models. And next, what we can do is we can call, using this function ANOVA, we can compare our ANOVA models. So when we compare the first model with the second model, so in the first model, all the difference was based just on treatment, whereas in another case on treatment plus age. When we compare these two, what it shows us is that the explanation by the second model is not significantly different than the first model. And that means that we can rule out that age is having an impact on cells that is apart from treatment. Yeah, so what this means is this p-value means that it's not really something that's having an additive effect. So whatever is the difference that can be explained by treatment, we cannot explain something more based on these two factors. We can also do this for the third one, right? So we can see if we say so let's just see how the third model looks, just to give you an idea. So to look at the model, we say summary. So in this case, we have 3 parameters: treatment, age, and the interaction of treatment with age. So is age playing a factor on treatment and vice versa, right? So is there some interaction? And now you can already see that treatment has very significant impact on cell, right? Because that is what we were modeling, is cell number changing based on treatment, age, or the interaction, whereas age and treatment and age don't really seem to have much of an impact, right? But you can also see this by comparing the 2 ANOVA models. And again, what you see is that when you compare the 2 ANOVA model, the second model doesn't explain more than the first. Yeah. So this is the way how you can rule out certain parameters, whether or not they are having an effect on your observation. Yeah. And I think also many people like to see the QQ plot, whether your models are normally distributed. So you can just say plot ANOVA model after you have made the model, right? And it is actually going to make 4 plots for you, in which the second plot is the QQ plot. So it is going to make, so here is the QQ plot, right? And in this case, at least the data looks normally distributed. So the residuals there is not so many residuals that are far away from this line. So what is residual? So I mean, ANOVA is a model, so it tries to make a predictive line. It tries to model it. So this is the predictive line, and the residuals are what cannot be explained from this line. So if you see a strong bias on one side of the line, that means that what cannot be explained might be because of the distribution of the data. It's because the data is skewed, right? But if it's randomly distributed along the line, it means that, well, we cannot explain everything, and what cannot be explained might just be noise. Yeah. So these are a few plots that we did not cover previously with ANOVA, but I think maybe people are interested how to compare ANOVA models and how to make these kind of QQ plots, right? And it also has a few other plots which I do not really understand completely, but if you are interested, you can have a look. And that is it. So if you have any problem in reading your file, making it into tidy, and at least getting to statistics, then do let me or Yura know. Both of us are available. You can just send us an email. But I hope that at least you can now start playing around with your own data, and you do not depend on other softwares, and you can move to R. And on Wednesday, it's we are only going to focus on plotting. So it's, I mean, we have a lot of things planned. Hopefully we can cover everything in 2 hours, but do install the things because of all the plotting needs new packages. So please have them installed. And with that, yeah, thank you. Thank you for your time, and then see you Wednesday. So Wednesday, 5 p.m., same time. It will all be about plotting. Thank you. Bye-bye.